end the workshop, the boot camp, and we are really honored to have Peter Bickel here to give this talk. So Peter is a professor of statistics here at UC Berkeley. So we're really glad that he's here. I specifically am very glad that he's here. And he's going to tell us about David Blackwell. Thank you.
Thank you. Well, thank you for inviting me. It's always a pleasure to talk about David. I intend to talk a little bit about David as a person, since I knew him actually in various ways. And then I want to talk a bit about the paper that, in fact, I gather is sort of at the base of much of the work of this boot camp, the vector minimax theorem. And but we'll get to that. So let me start by the obvious picture of it's one that I see hasn't been shown yet. But it's fairly characteristic. I mean, he's smiling, and that was a general characteristic of his. He liked life. All right. So first of all, let me also give some references. I think that you've gotten many more from other talks, but so the photo is the credit of George Bergman, who's a faculty member in mathematics here. And there are at least a couple of papers that I'm more familiar with, or books really. One called Mathematical People, which has a long interview with David, and another one, an earlier one, a conversation with David Blackwell in 1986 in Statistical Science. And both are really quite revealing. Well, here's some highlights very quickly summarized of his career. I see that I made a mistake, or at least a mistake was made for me, that he didn't live till 2020. He lived till 2010. And he started out, as you've heard already, educated at the University of Illinois. His talents were recognized quite early. His thesis advisor was Joe Doob, who's rather well known in statistical and probabilistic circles. And Doob took him with him to the Princeton Institute of Advanced Study, as Rakesh mentioned. And then after that, he went to Howard and finally ended up at Berkeley. Now, it's true that he was, as Rakesh said, the right person at the right time, but it's also true that he did have some difficulties. So in Illinois, he went to one of three high schools, one of which was all black, one of which was all white, and one of which was mixed. He was able to go to the mixed school. His teachers recognized his talents early. I hadn't heard before Bin's note that he was already recognized for his brilliance, but that's not surprising, really. But he went to Illinois originally planning to be a teacher of mathematics, a high school teacher. But there again, his talent was recognized. He got to his bachelor's quickly. I think he was encouraged to go on to the PhD by Paul Halmosh, who some of you may have heard of, and another guy, Warren Ambrose, both of whom were students of Doob's. And he finished his PhD quickly. Doob then brought him with him as a Rosenwald Fellow to the Princeton Institute, where everything went well at the Institute, but the math department in Fine Hall refused to grant him the privileges which were usually given to other Rosenwald Fellows at the Institute. However, he survived that, and he survived it because of this general attitude to life and research, which I think I would like to mention early, and I have always encapsulated it as David always thought that the cup was half full rather than half empty. He was a very, very positive person, and I mean, very kind, as others have heard, but he also just took life as it went. And in the end, he was rewarded with the honors that were his due, but it took quite a while. He made contributions in many fields, not only in approachability, but in renewal theory, in information theory, in logic, actually, towards the end. Of course, in statistics, the Blackwell theorem, but actually other even more significant contributions. And as I said, he had many honors. Okay, my contacts with him. I started out in 1959 or 60 as a student in his class in information theory, which was a wonderful class. And he did indeed give wonderful, clear lectures, as you've heard mentioned several times. But it compensated for a book I didn't like by Jack Wolfowitz, which was called Coding Theorems of Information Theory, and had as a subtitle I somehow recall, Information Theory for Mathematicians. To show that, you know, how pure it was. But now in retrospect, I think David may have chosen it because it enabled him to show his view of information theory, which was quite different. In any case. Okay, so that was the start. And then I didn't do my PhD with him, though I will tell you a story which is quite relevant to the paper I'm going to talk about. You know, I got my PhD. I became an assistant professor at Berkeley, and then, you know, I talked to David, and at some point, I was teaching a graduate course in statistical theory, and I came on a problem on something in his book, Blackwell and Girshick, and something in Eric Lehman's book on testing hypotheses, or destination book. In any case, I noticed something that might be interesting, and I went up to him and I talked to him for about an hour, and we concluded that we understood what was going on. And then he said, "Go write it up." so I think it was a gift to a young assistant professor. But in any case, the paper appeared, and let me tell you about it very, very briefly, because that's all it deserves. It's called a note on Bayes estimates. And there's a classic result which started this all, which is the following, which I think many of you probably know, that if x and y are such that both x squared and y squared have finite second moments, and the conditional expectation of y given x is x, and the conditional expectation of x given y is y, then x equals y with probability 1. That's the only way you can have that. And that actually can be translated in both probability and statistics. In probability, it's translated as a forward and backward martingale is constant. And in statistics, and that's where I started, is if a Bayes estimate with respect to quadratic loss is unbiased, its Bayes risk is 0. And that's what this paper is about. And what our paper was is simply generalization to unbiased and Bayes with respect to general convex losses, in particular the LP losses. And it turns out that for p strictly bigger than 1, it generalizes straightforwardly. For p equals 1, it's actually not true unless one puts a condition on. That's because the median is not unique. The loss is not strictly convex. Okay. Now, to my main topic. And actually, that's the reason that I, in fact, after some hesitation, agreed to speak, because, you know, I have various things, reminiscences of David in various places, and didn't see it necessary to do that again. But it turns out this paper has some significance for me. The analog of the minimax theorem for vector payoffs. And the significance is that when I was a graduate student, before I decided to work with Eric Lehman, I went around shopping for a thesis. I didn't have my own idea for a thesis, and I went around shopping for a thesis. And in particular, I went to David, and David showed me this paper and said, well, there are a couple of conjectures in here that you might be interested in. And I looked at it. Unfortunately, I had no idea what the von Neumann theorem was, much less the vector analog. I got a bit frightened, and also, I guess, there were other things I knew better. So I worked with Eric, which was wonderful too. Okay. So, but I decided, of course, why not finally find out what that paper is about? And so I read it, and it's really a delightful paper and very interesting. Okay, so the first step is that it's a dynamic formulation. It can be viewed as the von Neumann min-max theorem. So the von Neumann theorem is a one-shot deal, right? You have a randomized strategy, your gains or expectations. Well, David simply changed that into, you can have an infinite number of plays, F1, Fn, And then you look at the average gain. And in the von Neumann theorem, right, the gain, let's see, I'm not sure I get to it. Yeah, there's a payoff matrix, of course, Mij. This is all finite. David loved finite things. He was not too happy with, with great abstraction. So the dynamics is that you play an arbitrary number of times, n tending to infinity. You have strategies, F1, G1 for the two players. The payoffs are X1 through Xn, right? According to the matrix, depending upon what you play. Simple strategies you play each time, or the randomized strategies give you each time. And then you have the payoff at time k, and you can use probabilities as you please. And in fact, I should say they can be, nothing says that this suggests that they're fixed for all time. No, they can depend on, they can be Markovian, in fact. You want them to be Markovian. All right, so then you identify the von Neumann theorem as in this way. There exists a value V, right? And a strategy Fk, which is the same, you play the same thing each time, F star, for one such that the average tends to V, no matter what strategy to use, and vice versa. And you approach in some sense from above and from below, right? Okay. So what's the generalization he considers? He considers vector payoffs, right? Mij is in Rk. And you have a definition, which Rakesh gave earlier. Given a closed set S in Rk, and S is approachable if and only if there exists a strategy, F star, for player one, such that the distance between the average and the set S tends to 0. No matter what strategy two plays, right? So there's no max min anymore, but simply no strategy with two plays. But you still want to win, right? Which is get to S. S is excludable if and only if there exists a G star and a positive D such that basically you're kept away a distance D from S. Okay. So he has a more general theorem, but the theorem which I believe Rakesh quoted and which I think is the essential. Suppose you have general closed convex sets. By the way, neither closure nor boundedness are relevant. I mean, they both are without loss of generality. And the theorem, he says, is if S is convex, it is always either approachable or excludable. As you see, it extends to general, but not all sets, and that's a bit of a reason for my comment when Rakesh put down his initial statements, that it's not true in general. There's a closed set which is neither approachable nor excludable in this sense. There's a weaker sense in which every set is approachable or excludable. Okay. All right. First obvious remark is it's enough to consider approachability and excludability for player one, because you can just switch from M to M transpose for player two. And of course, intuitively, F1 star, F2 star, etc., are not independent. But what it turns out all you need to do for this purpose is to basically have the law of the average gain at time n+1, given the past gains, to depend only on the average gain given n+1. And then the same thing with the strategy. So in some sense, it's Markovian and Markovian given the average gain previously. Okay. Now here is, I think, the first key observation, which I haven't seen anywhere else. He makes an identification, a representation of mixed strategies as follows. Suppose that P, the vector, oops, what happens here? Oh, yeah. The vector P is a strategy for one, and the vector Q is a strategy for two, okay? The probabilities on 1 through R and 1 through S. The reward, R of P, is the set of all possible vector payoffs that can occur if one plays P. Right? So it's a set P transpose MQ where Q varies over the simplex. And similarly, there's that's R of P. Obviously, it's a convex polyhedron because it's a convex mixture of finite number of points. And similarly, you have T of Q, which is the same thing, but for player 2. And clearly, R of P corresponds is a way of coding all Q for every P. And T of Q is a way of coding all Q for every P. Oops. What happened? All right, so there's an obvious alternative representation of the game. 1 picks R of P, 2 picks T of Q, and the payoff is P transpose MQ. Okay. All right. Now I'm going to, I think, give a probably not new proof of the von Neumann theorem, but a proof of the von Neumann theorem using simply this idea of Blackwell's. Okay, so notice that in one dimension, R of P is simply a set of intervals, right? They're all, each of the R of P's is convex. So you have intervals A of P, B of P. And now you can turn these into half rays, right? Because it doesn't matter as far as, these correspond to Q's, right? B of P is a payoff from some Q. Right? It's a little bit confusing, but you can make them into half rays without any loss. Minus infinity to B of P, right? Which is the highest payoff that Q can get. Right? And similarly, the same for the Q intervals, T of Q, but there you move it the other way, D of Q infinity. Now, notice that R of P and T of Q is not empty for all P and Q, right? Because in particular, if it's Q that player 2 is playing, the one corresponding to P, the point corresponding to P is the total payoff. Right? So, furthermore, notice that if you make this identification, you have an ordering. If B of P1 is bigger than or equal to B of P2, our tilde of P1 contains our tilde of P2. That's the one where you extend to the end. And the same with D. And now simply let P star be the arg min over P of B of P. And Q star the arg max over Q. And P star and Q star assumed by compactness, the simplexes. And of course, R of P star intersection T of Q star is not empty. In fact, it's one point, which is the value. And those are the strategies. There may be more than one pair of optimal strategies, but we know that's always the case. So there's the proof. All right, so it doesn't require hyperplanes or any of that stuff. And the brilliance of it is that you translate this high dimensional problem into a one-dimensional problem. We can use the order of the line, which of course we can't use in general. Okay, so I don't know if that's one of the 5 proofs. May well be. Rakesh told me that there are at least 5 proofs of the von Neumann theorem.
Well, 5 elementary. So
this is pretty elementary.
well, those authors would object because of the appeal to compactness.
Oh, come on. Oh, you mean as far as general reliability goes? Well, I'm just talking about the old-fashioned 1928 von Neumann. Okay.
Would you mind, sorry, could you go back 2 slides where you defined, where you defined the field?
Yeah.
Right? The R's were 2, I think, previous one before that.
Okay.
So at the end there, where you say R
of P can be identified with the set of all Q's.
I see.
Right.
Got it.
It's a way of coding. I mean, again, you may have repeats and so on.
Yeah, yeah.
So, okay, there we go. All right, so it's out. I don't think I made any gross error. I think it's okay. Okay. All right. Now we go to convex S, and now we go to the vector case. Let's see if I- All right. The claim is that a necessary and sufficient condition for approachability is that the intersection of every one of the T of Q's with S is not it. Why is that? Well, remember that both T of Q and S are closed convex sets. So if they don't intersect, you can draw a hyperplane between them. And intuitively sort of clear that if they don't intersect for some Q, you just 2 will use that Q. Because no matter what P comes in, it's going to be in T of Q, not and stay away from the set. All right, here's actually somewhat more formal statement of what I just said. If T of Q0 intersection S is empty and 2 uses every time Q0, of course he doesn't get Q0 each time. He gets a pure strategy, a pure result each time. But this is obviously true. Xn bar minus the average of the conditional expectations of the output given whatever one plays, right? Because Q plays Q0 always, is going to, it belongs to T of Q0, right? That average belongs to T of Q0 because Q0 is played every time. Okay. Now, the other way is not so easy. And that's, suppose that T of Q0 is not equal to the empty set for all Q. Shouldn't be Q0, it should be Q. Okay. Then I won't go through the details, but you look at the ordinary von Neumann theorem, the one-dimensional one, applied to the games x minus y of x mij. Who's y of x? Y of x is the closest point to x in S. So it's again, you'll see a picture very similar to the picture that Rakesh had in his lecture. Then, by the ordinary von Neumann theorem, you can argue that there exists a P such that R of P is separated from X by hyperplane. And I'll show you the picture, I hope. Oh, I'm sorry, that's not the picture yet, not yet. Okay, so the strategy is actually the following. You use Xn bar, the average up to time n, to choose what randomized distribution you'll use next time. And if Xn bar belongs to S already, it doesn't matter what you do. But if Xn bar is not in S, you find Y of Xn bar closest to Xn bar in S, right? The closest point. And then you proceed according to exactly the picture with the Rakesh drew. And here it is. Not quite as neat as Rakesh's, but it's the same picture, right? Here is S, here is T of Q, here's Xn bar, here's the foot of the perpendicular, here's Y of X, right? Here's everything is on one side. And basically, what you go for is you go to the T of Q intersection S closest to Y of Xn bar, which is on the first one you hit, that'll do it. That corresponds to a P, right? Because T of Q is just the set of all P's. All right, and here's a heuristic. And now again, this comes back to Rakesh's very nice presentation. if x does not belong to S, and y of x is the closest point on the hyperplane, then here's the hyperplane, right? The equation of the hyperplane, y minus x eta equals y minus xy, because y is on the hyperplane. Y minus x is the perpendicular. And for all 8 on 8 on h, or on the other side to x, you have this inequality. Finds that side of the hyperplane. And then you have a sub-Martingale type property, as Rakesh mentioned. It's approachable no matter what q is used each time by 2. If un is y of xn bar minus xn bar, right? Then the conditional expectation of un xn plus 1 given x1 xn is bigger than or equal to un y of xn bar, right? That's simply stating exactly the fact that the thing is on the other side. That you're on one side of the hyperplane and the other thing's on the other side of the hyperplane. And then you use the fact that, of course, for any q, T of q intersection S is not empty. And then, this I'm now following David's argument. If you define delta of n to be the square distance between y of xn bar and xn bar, then you don't have quite a semi-Martingale. You have a little bit extra, but not much, right? Here's the semi-Martingale property plus c over n squared. You just make the computation, but that's always the case. And from that, you can deduce the delta n sub tends almost to 0 by this theorem that Rakesh cited. So there's some interesting consequences, which I'll just mention again. These are things that David noted. R of P is always approachable. That's always an approachable convex set because R of P intersection T of Q is not empty for all Q, obviously. Again. And then there's a connection with von Neumann games. S convex is approachable if and only if the value of a certain scalar game is bigger than or equal to the minimum of US, capital S. That's, again, this related to this hyperplane property. And the scalar game, maybe I should clarify. UM means it's the inner product between U and M. M, if you remember, is a vector. U is a vector. So that's a scalar.
What is M? M is there M there?
I'm sorry. M is the payoff matrix, but the elements of the payoff matrix are vectors.
Got it.
Okay. All right. I think I'm going to end quite early. All right. Which I'm sure you will. Okay. All right. So David has his conjecture in this paper of his. And the conjecture was that, I'm sorry. He gives an example, which I will not give you. I refer you to the paper, of a set which is not convex, which is neither which is both, well, neither approachable nor excludable. But he has this conjecture of a weaker notion of approachability, which is actually improbability, if you want, rather than almost surely. Again, you want a sequence of Fs and x1, xn, which come from 2 strategy, such that for all n bigger than or equal to something which depends on epsilon, delta, and s, the distance, that's what this is, the distance between xn bar and set is less than or equal to, is bigger than 1 minus delta. But doesn't say anything about the point sticking there, right? It's an improbability inequality. It's not a union or an intersection. And similarly, weak excludability means with high probability, you have to stay outside instancy. Okay, and he has this conjecture that every closed set, and closure doesn't really matter because delta of xs is the same for delta of xs and delta of x bar. That in fact, every set is either weakly approachable or weakly excludable. And indeed, that conjecture was proved by a man named Nicholas Ye in 1992 using differential game theory and all sorts of fancy stuff. Now, I think I mentioned to you that David pointed to this conjecture when he suggested that I work on this paper. And so I think there must be an elementary proof, because David would not give a thesis problem, unlike some of us, unless he basically knew how to do it. So I thought I had an elementary proof, but I don't. I think maybe I'll be able to get one, but certainly this was not an elementary proof. And that's it.
Are there any questions?
Rakesh.
The argument you gave involves basically projecting down to the set of payoffs,
Yes.
and that makes it a real line. So why does that argument break down here?
Oh, because the vector space is not ordered. Only the line is ordered. Because I can take the inf
I see.
of the piece, of the tips of the
Right.
of the columns. It's enough. General inflection. But there may be some variant of that. I mean, I think the idea of identifying these sets is a nice one. I think it may have applications more better. But anyway, as I should have told you, by the way, that I am, since I did not follow this line, I've worked on some David's stuff. I've been very interested in sequential analysis. I know the Girshick Savage paper, Blackwell, Girshick paper, but this is completely new to me. So I apologize for the state of the office.
Are there other questions?
A historical question.
Yes.
I'm from Illinois and I've talked to Jordan many times, but I haven't been alive. I was curious what Duke famously was very anti-information theory, and you said you took information theory from Blackwell, and later he changed his mind. I was wondering if Blackwell had any role.
I didn't know that Duke was anti-information.
Yeah, you wrote an article. It kind of.
Oh, no, right. I remember.
He said I think Shannon's proofs were very handwritten. It was all correct.
Yeah.
But he would just appeal to the law of large numbers and stuff.
Right. Whereas Kolmogorov actually appreciated it.
Yeah, exactly. And then and Duke changed his mind.
Yes. I remember now. I remember that story.
Blackwell.
Yeah, I think. Well, first of all, I think Blackwell did information theory later. I mean, he didn't get to information theory until he did this, as I think Rakesh mentioned, the Shannon, Ryman Shannon. Oh wait, is he involved in that? Yes. The information theory, the Shannon coding theory.
A much better, I think that's
Yeah,
not.
Shannon. Yeah, it was not Black. But yeah, but everything he did. I mean, he certainly had papers in information theory. There's something called the Blackwell channel, I believe. I don't know exactly what it is, but but I think certainly his thesis, I believe, was on Markov chains. And I think I told somebody, I really do believe it. I talked to him, and he wasn't to work. Somehow, deep down, everything had to do with Markov chains and games. But anyway, but certainly he had no objection to information theory. In fact, that course was a bit of an anomaly in the SAT department. It should have, in some sense, been taught in electrical engineering, but I think he created it.
Are there other questions? I have a historical question too,
Yeah.
but I don't know if it's the right question. I'll ask
Please,
it anyway. I'm wondering if you know what drew him to look at vector payoffs in games in general. There was a talk earlier as well that was, I think there was a quote that he was driven a lot by thinking about war and fighting it and stuff.
Yes, I remember
Is
that.
this one
I
of
didn't,
them?
as I said, this is not, I mean, I just viewed it as part of his general interest in games. But I think it was Ben or someone that mentioned. He met Girshick, I don't know if he met Girshick at Rand, but they certainly worked together at Rand a lot. And that's what Rand was about. Rand was figuring out how to play war games successfully. I remember I actually had a flavor, not that, a classmate who worked on the summer at Rand. He was American citizen. Wasn't so good. But he worked with somebody named Entov, who played games. I was always suspicious of it, continue to do. So that's, I think that's probably right, yeah. But I was surprised, really very pleased to see the broad spectrum of applications of these ideas.
Yeah, that's why I was wondering, because it's easy to look now and see how impactful it's been, but it's always easier to do it 50 years
That's
later.
right. Well, another example, I think, of something like that, which I was thinking of maybe talking about, but decided to, this instead, since I didn't worry about it, was the arrow Blackwell backward induction. Again, it was a way of proving the optimality of sequential probability ratio tests in a longer, transparent, and general way. Whereas Wolfowitz and Wolf had proof at about the same time, but which had not a Wolfowitz. And that again, I think is an idea which is, I guess, dynamic programming was actually Bell, right? It was not Blackwell, but Blackwell was certainly involved in it at a very early stage. Okay, thanks.
Thank you so much. Thank you so much, Peter, for a great talk. Well, this brings us to the end of today and end of the workshop. Sid wants to say a few words about what to expect.
Yeah.
Do you want this?
No, this is fine. I guess firstly, this was amazing. Like, we started off planning this, and all we did was we kind of identified a bunch of people and asked them if they would be willing to talk. And many of the speakers today, or several of the speakers, have just come down just for this day. And like, we didn't really say too much about it. It was more, we want to do a day in honor of David Blackwell. And it's like, I'm deeply satisfied with how it's turned out. I think we learned a lot from it. So a big round of applause and a big thanks to all of the speakers. And I guess overall, this was a fun boot camp to organize. So I also want to thank my two amazing co-organizers, Nika Haktalab and Adam, who is somewhere flying back to LA, but will be back next week. So let's clap loudly enough so that he can hear us. And yeah, this sort of gets our semester off to a really nice start. So the plan for the semester, kind of paraphrasing what Ben was talking about, we have, we have a lot of commonality. So somehow many of these ideas have been taken on by a lot of different communities and taken off in different directions. So we tried getting people from across many different communities, but hopefully everyone can come and tell us all the simplest unknown question or the simplest open questions they have. And then in the spirit of Blackwell, we can all sort of get together and think deeply about it. And we will have a few more workshops. So I think the next workshop is being organized by Theodoris, Laura and Kevin, and this is in 3 weeks. Is that right? Or September 12th. And roughly speaking, the 3 workshops that we have they're all about sequential decision-making processes, but like thinking about the information structures first, then the constraints, and then the objectives, and how all of these have come together to influence the way we think about these processes. So I hope to see all of you all at these workshops. And also the next week, we have another program in parallel on graph limits, and there will be a bootcamp next week. So if you all aren't tired of talks, we have way more talks if you can come and attend. But on that note, I should stop talking. Thank you. Oh, okay, I guess Theodoros has something else to say.
Just a reminder, there is a town hall next Monday, 1 p.m. to get the program started.
Yes, so we'll have a town hall to decide what all we should work on next Monday. You'll get lots of emails on this and Slack messages and all other such forms of communication. But I think for the moment, we should stop and just reflect on all the things we've heard about today. And so thank you everyone for coming, and see you all.